Hello student, my name is Nimesh Prabhakar. I am Assistant Professor at LJ Institute of Engineering and Technology in Instrumentation and Control Department. Welcome to Process Control Lecture Series.
In my previous lecture, I complete chapter number 2, Heat Exchanger, Dynamic Behavior of Heat Exchanger. Now we start chapter number 3 and 4. Because the topic of chapter number 3 and 4 are interrelated, so we see both now. So here in this lecture we discuss about the linearization of system, then deviation variables, then after we discuss about the date time, and lastly we discuss about the self-regulating process. So now we start linearization of system. So first of all, question occur in mind, what is linearization? So answer of this question is, linearization is the process by which we approximate the non-linear system with linear ones. That means linearization is a process in which we convert or approximate the non-linear system into linear system. That means linearization is, in a simple word, we can say linearization is a process in which we convert non-linear system into the linear system, or we approximate the non-linear system into linear system. So this is a definition of the linearization. Now another question occur in mind, why we require linearization, or in other words we can say why we have to convert non-linear system into linear system. So the answer is, most physical systems exhibit non-linear behavior, while characterization of dynamic system by transfer function can be done only and only for linear system characterized by linear differential equation. That means most of the system in the chemical industry or in other industry like in a process control, their behavior is always a non-linear behavior. 99% system have a behavior non-linear behavior. So to apply Laplace transform or to find out the transfer function, we must require this non-linear system to convert into linear system. So that's why we have to study linearization of system, or in other words, we require the non-linear system convert into the linear system. So it is important then that the non-linear model we linearize for control system analysis and design purpose. So for control system analysis and design purpose, we have to convert non-linear system into the linear system, or we have to approximate the non-linear system into linear system. So now we start the process of linearization of system. So in other words, we can say the steps of converting non-linear system into the linear system. So therefore we consider the non-linear differential equation. So suppose we have one dynamic system, and this system have one non-linear equation. The equation is non-linear differential equation is dx by dt is equals to fx, is one equation of one dynamic process. Now we expand the non-linear function fx into Taylor series around the point x0. So in this we use the Taylor series expansion. So now we expand fx with respect to point x0. So we can write by using a Taylor series expansion, fx is equals to fx0 plus df by dx x0 x minus x0 1 factorial plus df square by dx square x0 x minus x0 square 2 factorial plus up to df raised to n dx n x0 x minus x0 raised to n factorial. So this is simply we use the Taylor series to expand the function of fx. Now here, if we neglect all term of order 2 and higher, we take the following approximation for the value of fx. So now here we neglect this all term, that means a higher order term. We only consider this term fx dfx by x0 x minus x0, and now we neglect these all terms. So here we can say the fx is nothing but approximately fx0 plus df by dx x0 x minus x0 1 factorial we can write. So we can give this equation as equation number 3. Now this is our equation number 3. Now it is well known that the error introduced in the approximation 3 is of the same order of magnitude as the term I is equals to df square dx square x0 x minus x0 square 2 factorial. So this term is indicate the error term. So here we can say by graphical we can understand. See, this is the behavior of a dynamic system this is the equation number 1 we have written. So this is a function fx and their behavior with respect to here the x and here the fx. So this is a non-linear system we can see here, but here we have taken the Taylor series expansion. So we can see here this is a tangent at the x0 point. So we can see here the x0 point, it acts as a linear system. This is a x1 point, but here x1 point it acts as a non-linear system, we can see here. So we can write the approximate behavior of a non-linear system at x0 point by using this equation. So that's why we can say if we add the second order differential term in this equation or the Taylor series, the error is introduced in the equation. So that's why we neglect the other terms and we try to convert this non-linear system into linear system. So this term is known as the this term introduced error in the system. So the linear approximation of equation number 3 is satisfactory only when the x is very close to x0, where the value of term I is very small. See here, the behavior of this system is approximately linear, but when the x, this function x is near to x0 value, because when this is a non-linear we can say. So this is possible because at that time here the error term is very small, so we can write this term. So in the figure we can see the non-linear function fx and its linear approximation around x0, and the linear approximation depends on the location of x0 around which we make the expansion into the Taylor series as we discussed above. So in equation number 1 we replace the value of fx by its linear approximation. So we can write the equation number 1 as, by using equation number 3 we can write equation number 1 as dx by dt is equals to fx0 plus df by x0 x minus x0. So this equation is represent the linearized approximation of the equation number 1. So this is a method of linearization or the steps of linearization of any non-linear system. So this equation is represent the linearization of the non-linear equation, that means equation number 1. In equation number 1, we have just simply put the value of fx by using Taylor series expansion. So by using Taylor series expansion, we can convert non-linear system into the linearization, or we can make the approximation of the non-linear system into linearized behavior. So this is a matter of linearization of system. Now we discuss about the deviation variable. So in chapter number 1, we discuss about the different types of variable, inputs, outputs, and other variable. So now another variable comes. So this is a deviation variable. So what is deviation variable and what is the use of the deviation variable? The first question come in your mind. So now we see. So to understand the deviation variable, we consider the non-linear differential equation that we already considered in a linearization equation, same as dx by dt is equals to fx. Now suppose that the xs is the steady state value of x. That means we know the x is the one variable, and if xs is the steady state value of that x, that means x variable, so we can write this equation as dxs by dt is equals to 0, because we know at the steady state the differential is the 0, because at that time the input is equals to output. That means no accumulation or no variation. So at that time we know the system is constant and the differential equation of the constant is 0. So that's why we write the steady state value dxs by dt is equals to 0, and we have given the name as a fxs. Now, so by nonlinear approximation, by using a Taylor series expansion, we can write this equation as nothing but in terms of dxs by dt is equals to fxs plus df by dxs xs x minus xs. So here we have expanded this equation with respect to the xs point, and in that case we have expanded system with respect to x0 point, but here we expanded with respect to xs point. So that's why we have write this. Now we subtracting equation number 2 from equation number 3. So we can write dx minus xs upon dt is equals to df by dx x0 x minus xs. That means this fx and this fx term is 0, and this is the difference between those. So we can write x minus xs here. So now here we consider, if we define deviation variable x as x is equals to x minus xs. Now we define this is a term as a deviation variable, as so we represent the capital X is equals to x minus xs. So then we write the equation number 4 become, so here we simply put the we simply put the value of x instead of this x minus xs. So we can write the equation number 4 as a dx by dt is equals to df by dx at the xs point, and this is we replace the x and this is a x. So the equation number 5 is the linearized approximation of the non-linear equation expressed in terms of the deviation variable x. So this is nothing but the linearization of the non-linear equation with deviation variable. So this equation is represent the deviation terms in the linearization non-linear approximation. Now we see the date time. So to understand the date time, we first take one example. So here we consider one pipe. In this the water is flow, and this is the inlet water temperature and this is the outlet water temperature. and UAV is represent the velocity of the fluid or the velocity of the water, and this tube length is L, we consider it. So now we start. Consider the flow of an incompressible non-reacting liquid through a pipe at T is equals to 0. That means at here T is equals to 0, the temperature of the inlet change as shown by curve A in the figure B. That means here we increase the temperature. So at that time, the behavior of the temperature with respect to time here represented by the curve. So here we can see by curve A the behavior of the temperature. Now it is clear that temperature of the outlet at T0 will be remain the same until the change reach the end of the pipe. That means at that time the behavior of the outlet temperature is not changed. At T is equals to 0 time, the temperature change effect only on here the inlet side. That effect reach at the time at here at some time difference. See here at T0 is equals to time, the temperature we can see here, and after some time this temperature difference is come here. That means it takes some time. So this time is known as dead time. So we can say then we will observe that temperature of the outlet changing as shown by curve B. So here curve B is represent the temperature of outlet changing. So from the figure we notice that the change of outlet temperature flow the same pattern as the change of the inlet temperature, but with the delay of time TD second. That means this outlet temperature follows same pattern of the inlet temperature, but after some time delay. This time delay TD is known as dead time. So TD is the dead time, and it is expressed as the equation of dead time is volume of the pipe upon volumetric flow rate, and we know the volume we can find by using the area multiplied by L. So A dot L, and the volumetric flow we can write area into the average velocity of the fluid. So here A is constant, so we can write that L upon UAV. This is nothing but the time delay representation. So where the UAV is represent the average velocity of the fluid, and functionally we can relate T in and T out. That means the inlet temperature and outlet temperature we can relate as T out is equals to T in into T minus TD. That means this is a time T and this is a dead time or the delay time. So we can relate the temperature outlet with the temperature inlet with the dead time. So this is the dead time. Now we see the self-regulating process. So what is self-regulating process? So a process is said to be self-regulated if a specific value of the control variable is added up for a nominal load with no control action. That means we consider one process, and due to some variation that process change its behavior. Okay, now after some time automatically that process achieve its desired value. That means we consider one variable that vary with time, but after some time that variable achieve its desired value without any controlling action. So that's why we know this system as a self-regulating system. That means here we do not require any controlling action to achieve or to achieve the desired value of the variable. So this type of system is known as a self-regulating system or self-regulating process. So example of self-regulating process is one based is the thermal system, because in a thermal system there is a certain temperature of a particular heat input. Now due to disturbance the system will acquire another temperature, but it will not go out of control. That means after some time the temperature that is vary is converted. After some time this system is automatically regulated. So that's why here we do not require any type of control action. That means here the temperature difference for the temperature difference we do not require any controller. So that's why we know as a thermal system as a self-regulating system. Now we see the another example of a not self-regulating system. So here we see a liquid level control system. We discussed about the liquid level tank system in chapter number 2. So liquid level control system in which the outflow is through a pump is not a self-regulating process, because here we require one controller that controls the inlet and outlet flow. So that's why this is not a self-regulating process, because because in the liquid level tank system we have to control the liquid height in the tanks, and to control the liquid height we require one controller that controls the inlet and outlet flow. So that's why the liquid level tank system is not self-regulating system or process. So if the inflow is equal to outflow, then the level remains fixed. Since the outflow in this type of system does not depend upon the head, the liquid is pumped out at constant rate. So in case of increase or decrease inflow, the tank will overflow or go empty. So that's why we require one controller for controlling action. So this is a self-regulating process. Okay.